Good day, everyone. We're reviewing Wetzel's Limnology textbook, edition number 4, chapter 7, and we are working on the fate of heat in lakes and rivers. And more specifically, right now, we are looking at heat budgets in lakes. So let's jump right in. The surface energy budget and stratification. The diel patterns of heating and cooling recorded in the upper water column of lakes results in part because solar radiation penetrates into the water, whereas the heat losses from evaporation, conduction, and net long-wave radiation are restricted to the upper few centimeters of water. When incoming solar radiation exceeds heat losses and when wind speeds are low, the water column is warmed, creating stable stratification in which less dense water overlays cooler water. In contrast, when solar radiation is less than the sum of the heat loss terms, the near surface becomes cooler, leading to unstable stratification in which denser water overlays less dense water. This condition is conducive to mixing by penetrative convection, a process whereby thermal plumes or convection cells form when surface waters cool, becoming denser and sink. The associated mixing occurs at night and when surface water cools during shifts in meteorological conditions, such as when cloud cover increases, wind increases, leading to increased evaporation, cold rain falls, or seasonal decreases in air temperature. At night, this mixing can erode the diurnal thermocline, and in cooling season, it contributes to the erosion of the seasonal thermocline. The thermal structure of a lake over an annual cycle is related to the energy budget. As illustrated for North Temperate Lake Mendota, Wisconsin, net radiative heating begins in January and peaks in July. Since the lake is cold following ice-off, conduction is initially positive as air temperature is warmer than surface water temperature, and conduction becomes negative in summer as the lake warms. Evaporation becomes a progressively larger heat loss terms as the lake's surface water temperature warms. The sum of these terms, the net heat flux, indicates whether the lake is gaining or losing heat. Net heat flux becomes negative by late summer. While Lawrence Lake is smaller than Lake Mendota, its annual cycle of heating and cooling follows the pattern established by the surface energy budget. Similar correspondence between thermal structure and the surface energy budget is found in lakes at other latitudes. For Ross Barnett reservoirs in subtropical Mississippi, the monthly surface energy budget is similar to that for Lake Mendota, but with reduced seasonality. Evaporation and conduction are important components of the heat budget throughout the year. Patterns of diel over diel and seasonal cycles are included for Arctic and tropical lakes in section 2D, with the additional inclusion of lake numbers, section I1D, to illustrate the influence of wind on mixing across the thermocline. So before we move on, let's look at some of these figures here and pictures. So figure 7.7-7, conditions conducive to heat input to a lake from condensation. As air above the lake becomes cooler, saturation levels of water vapor decrease and water condenses at the surface. Condensation releases heat. So what we are seeing here is we can see there's a little bit of a fog layer here. So the air above the lake right now is becoming cooler, and so therefore the water that is contained in that air is condensing, is creating this thin water vapor, the visible water vapor, which is pretty much like fog, at the surface. And that process here releases heat actually to the environment, to the air. So here we have two lakes or reservoir. So the first one is Lake Mendota in Wisconsin, and then the second one is Ross Barnett Reservoir in Mississippi. So one is in Wisconsin, as we said, and the other one is in subtropical warm polymictic. So this is dimictic. So that means that it goes through two turnover over a year period, and this is polymictic. So it may go through more than two. So in the y-axis, we have heat flow in watts per meter square. And so this is the zero origin, and this is negative. So where we have negative is flow, so where it's basically pretty much getting cooler, and this is where it's getting warmer. And on the y-axis, we have a year. So we have all the months during the year. And then what is graphed are like net radiation, heat stored in lake, conduction, evaporation. So evaporation becomes a process that is important, and as we just saw above, evaporation releases heat, and it starts at about April, and it ends in early December. So where the lake is releasing heat to the environment. Heat stored in the lake. So here we have two phases, right? So we have the first phase where the heat stored in the environment is the highest. So this is in May, June, and then it decreases and it becomes the lowest in November, and then it increases again. And very likely that lake freezes over. And so this is why right at that point here, the heat that is stored in the lake increases, because there is no way for that heat to escape because of the presence of an ice layer. Conduction. So conduction is hovering around zero up to February, then it increases slightly, and then it becomes quite negative all the way to late fall. And then the net radiation. So this is the radiation that is generated by the lake, I believe. And so it's the highest right around the summer solstice, like around June, July. And then so it's a typical bell curve. So kind of a different configuration for this lake actually it's a reservoir in Mississippi. So we have the same pattern for the net radiation, but otherwise pretty much everything else is different. So heat stored in lake. So we have quite a positive flux, and it crosses the y-axis right around, let's see here, right around August, where for here it crosses the y-axis around August as well. So it's probably driven by the amount of sun radiation, solar radiation that it receives. The conduction, however, is always negative. We don't have any any excursion into the above zero for heat flow in watts per meter squared. And then evaporation is actually a process that is occurring throughout the year and at different levels. But it's still, we don't have, like here we have where we have a period like in the winter where it's not happening, where here it's happening all the time because the lake probably doesn't freeze over. So let's see. Let's see what they are saying here. All right. Annual surface energy budget for dimictic Lake Mendota, Wisconsin, USA, and Ross Barnett Reservoir in Mississippi. And heat flow is equivalent to heat flux, and net radiation is the sum of SW net and LW net. Note the synchrony of heating and cooling and the rate of heat storage in the surface energy budget of Lake Mendota with the annual cycle of stratification in Lawrence Lake. The monthly means of evaporation, latent heat flux, and conduction in the subtropical lake have less variability than those for the temperate dimictic lake. As the water depth varies from 4 to 8 meters and winds over the lake are frequently high, even though water temperatures increase in the summer, the lake frequently mixes and has a mixing regime classified as warm polymictic. Additional sources of heating and cooling. Heat fluxes associated with ice. Fluxes of heat occur with the formation and loss of lake ice. When water at 0 degree centigrade freezes, 3.34 by 10 to the 5 joule per kilogram of heat are released. And conversely, when ice at 0 degree melts to water at 0 degrees C, an equal amount of heat is absorbed. In addition, and as ice sublimes to water vapor, 2.62 by 10 to the 4 joule per kilogram is absorbed. Once ice has formed, its albedo, that is the reflectance, can be high, as the high surface is if the ice is white, as occurs when there has been an interaction of ice and snow, or the surface is snow covered, and is lower when the ice is clear. The transmissivity of light through ice also depends on the clarity of the ice. When the ice is clear, KD can be similar to that of lake water, whereas transmission can be considerably reduced with white ice, for example, high KD. When the ice is clear, water below the ice can be warmed by solar radiation. Algal growth can occur, and depending on the stratification and incoming solar radiation mixing, can be induced by penetrative convection. Heat losses and gains associated with the sediments. Sediments of lakes absorb heat from the water during the warmer periods of the year. However, this component of the heat budget is generally small compared to the direct absorption of solar radiation by the water. That said, for shallower lakes, and depending on the magnitude of KD, the heat budget of the sediments can be significant. Sediments in shallow regions of lakes can absorb quantities of solar radiation, and some of this heat may be transferred to the water of timescales of a day, and heat losses from the sediment at night can create convective motion that induce mixing. Under ice, heat accumulated over the summer is released by the sediment and heats the overlying water, with implication for circulation and thermal structure. Few detailed studies of sediment heat fluxes over annual periods are available, making those from Lake Mendota particularly notable. Temperatures of surface sediment at a location where the water depth was 8 meters closely followed the annual cycle of the epilimnetic water temperatures. This thermal variation is attenuated with depth in the sediments, so that at a depth of 5 meters into the sediments, seasonal oscillations were muted. A similar relation was observed in hypolimnetic sediments at a depth of about 23.5 meters, but the amplitude of the temperature changes was reduced. Changes in temperature of the sediment lagged those in the hypolimnion, and the lag increased by about 1 month with each 1 meter increase in depth measurements. The heat flux between the bottom sediments and water can be approximated by the temperature gradient over a sediment water boundary layer of a distance ZSED. So QS is equal to KW by TS minus TW over ZSED, where KW is the thermal conductivity in watts per meter per degree centigrade, TS is the sediment temperature at the lower edge of the boundary, and TW is the water temperature at the upper edge of the boundary. As noted in figure 7-9, ZSD can be 5 meters. For purposes of modeling the temporal variation in the sediment temperature, profiles are included, and the seasonal temperature variation are assumed to be damped at a depth of 10 meters below the sediment water interface. So figure 7-9, annual temperature curves 0, 1, 2, 3, 5 meters with the sediment of Lake Mendota, Wisconsin's means for 1918, 1919, and 1920. Left sediments at a water depth of 8 meters, and then right sediment at 23.5 meters. So let's see. So what we have here on the y-axis, we have the temperature in degrees centigrade. Then on the x-axis, we have the month. And here there's a bar that shows like that there is ice at the surface of the lake. So between January and March, late March, there is ice on that lake. And then it shows the change in temperature at 8 meters. So for the years of for the annual temperature curve at 0, so this is 0, 1, 2, 3, 4, 2, 3, 5 meters. So these are like the depth at which the temperature were taken. And then these are, so therefore they are the depth as well as the means for values that were taken about more than 100 years ago in 1918, 1919, and 1920. And so what we can glean from that is that there is a highest level of variability in the temperature of the sediments at the shallow depth, and for Lake Mendota, and for the same lake, but at the depth of 23.5 meters, the sediments here, we have that being a little muted. So this is at an 8-meter water depth, and this is at 23.5-meter water depth. So meaning by that, there is, like in this case, there is the sediment starts at 23.5, so the 0 is 23.5, and so the 5 value would be then 28.5 below the surface. Where here, the surface of the sediment is at 8 meters below the surface of the water. So this is a shallower part of the lake compared to the deeper part of the lake. And so this is why we have pretty strong influence and a pretty strong variability in the temperature, because the sediments are closer to the surface, and so therefore receives a fair amount of input from solar radiation. All right, so let's see here. We are done with this part, and let's go into geothermal heating. Geothermal heating. In regions with tectonic activity, sediment temperatures can be higher than water temperatures at depth below the surface, and water from hot springs may also flow into the lakes. Examples include Lake Kiwu in Rwanda, Lake Rotorua in New Zealand. Geothermal heating in volcanic lakes can create strong convective currents that disrupt the seasonal stratification cycle or mix the hypolimnion of deep lakes. Indirect heating can also be significant in deep lakes. Figures illustrating the influence of geothermal heating are included in section 2C and 2D. Geothermal heating also occurs within the subglacial lakes of Antarctica and contributes to horizontal and vertical circulation in these water bodies. Heat fluxes from incoming and outgoing streams. Incoming water from streams, rivers, or groundwater can either be warm or cool the receiving water. The inflow term, Qi, is usually only important in lakes that receive significant percentage of their volume from surface runoff, either during one storm event throughout a rainy season or when there is considerable snowmelt flowing into the lake. Small or shallow lakes reservoirs that have short retention times and canyon reservoirs are likely to be affected. Heat can also be lost through outflows, Q0. For example, when warmer surface water is transported out of the lake, some hydroelectric and drinking water reservoirs release deep, cool water in summer months, which leads to warmer mean annual temperatures than if the deep water was retained. The effect of incoming water on the temperature within a lake will also depend on the extent to which the water spreads and mixes laterally, as quantified by the term horizontal dispersion, relative to the speed with which it exits the lake. Timescales for these processes are included in Chapter 8.2b. Consequences of spatial variability of heating and cooling. Advection can be caused by greater heating, cooling, or wind-driven mixing in different regions of the lake. For example, shallow areas may heat or cool more rapidly, and exposed regions may be more affected by wind and cooler due to the combination of deeper mixing and higher latent heat fluxes. In large lakes, spatial variations in the surface energy budget may occur. These spatial differences in heating and cooling causes density differences, resulting in density-driven flows. Overflows are expected from location where density decreases, as when heating is greater at temperatures above 4 degrees centigrade, and underflows originate from location where density increases, as when cooling is greater at temperatures above 4 degrees centigrade. The likelihood of such flows can be determined if meteorological and time series temperature measurements are taken at more than one location on a lake, and the resultant flows computed from the differences in the energy budget or the heat budget. The differences in the heating of sediments at different depths or location can also induce density-driven flows. Spatial variations of temperature within the sediment at similar water depth can be due to the type of adjacent landforms in the basin, and also vary with proximity to the shore, sometimes being warmer near shore and sometimes offshore. Shallower lakes may have greater overall sediment heating. Sediments heating overlying water can also cause vertical mixing by convection. Density-driven flows occurring under the ice in winter are describing, in section XYZ. All right, so I think that does it for today. Thank you for sticking on with me, and we'll see you next time.